Good morning, everyone. I'm Sundar from UCL, and I'll be presenting our work on attribute inference attacks against synthetic data. This is joint work with Andrea Gadotti and Rocher from the University of Oxford. In recent years, there have been many applications of synthetic data, including from companies such as Microsoft and also government bodies such as the National Health Service in the UK and also the US Census. But what is synthetic data? In synthetic data, we take some raw sensitive data as input and output a fresh synthetic data set that mimics the raw data set both structurally and statistically. The main difference between synthetic data and other forms of anonymization techniques is that the individual records in the synthetic data may not necessarily correspond to any of the original records present in the raw data. For this reason, synthetic data is often considered a safe replacement for raw data that can then be released to data analysts who can learn the statistical patterns of the raw data without incurring the same level of information leakage. Previous work evaluating the privacy of synthetic data has found that, firstly, that it can be a promising solution for private data release. However, more recent work, such as the one by Stadler et al., have also pointed out that synthetic data on its own does not protect specific outlier records from inference attacks. In our work, we find that the prior privacy evaluations of synthetic data has three main limitations. Firstly, positive privacy evaluations of synthetic data tend to rely on the memorization of whole records in their privacy metrics. However, in the real world, information can leak in much more complex ways than this. Secondly, there's a trend to focus on specific outlier records when trying to evaluate the privacy of synthetic data. However, it is currently unknown whether even average users can be susceptible to such inference attacks. The third and main limitation is that for specific inference attacks, which we refer to as attribute inference attacks, where an adversary aims to infer a sensitive attribute of a target record based on the non-sensitive or public attributes, separating out the population-level inferences between different attributes. For example, whether you have a disease and your ethnicity can sometimes be correlated, and separating out these population-level inferences, correlations from the individual-level information leakage has been hard to do in prior work. For this reason, in some instances, researchers have found that an adversary can still learn the sensitive attribute of the target record even without access to the underlying synthetic data. For these reasons, in our work, the primary research question that we are studying is whether synthetic data can protect even the average user or the random record in the raw data while providing sufficient utility for data analysts. In order to do so, we designed a new attribute inference privacy game that formalizes this risk of attribute inference, which I referred to earlier. To that end, we also designed a new evaluation setup that solves the fundamental problem of prior privacy evaluations, which is the base rate problem, where the population-level inferences are hard to separate out from the individual-level information leakage. The main intuition that we use in our game is to randomize the secret attribute or the sensitive attribute of just the target record. So an adversary without access to the sensitive data can only perform up to random chance when inferring the sensitive attribute since it's randomized and the population-level correlations are broken just for the target record. In our setup, we follow anonymization techniques and how those techniques have been evaluated by previous work. And we split our raw data into some public quasi-identifiers and the private secret bits. We then choose a random record and flip the secret bit, in this case disease, randomly for that specific record only. All other records remain untouched. Then some synthetic data algorithm is fed on this target data, and in our work, we consider a partially informed adversary. The adversary, in our case, is not only given access to the synthetic data, but also the quasi-IDs or the public information of the raw data. We note that this is a stronger setup than what is typically considered in the auxiliary information setup that is typically used to evaluate the privacy of synthetic data. However, we justify this in the case of multiple data releases, which are becoming increasingly common in the context of synthetic data. Furthermore, this is also a weaker setup than the differential privacy setup, which requires an exact knowledge of all the other records that are present, whereas we only assume knowledge of the public quasi-IDs. The last thing I would like to note here is that although it seems like the synthetic data has the same number of records as the target data, in reality, because we are sampling the synthetic data freshly, they can have a different number of records in the synthetic data as well. Data analysts can choose to include more synthetic records or less synthetic records, but the idea is that this process should protect against all of this as well. Our attack follows the simple intuition that simple statistical queries on the synthetic data needs to remain accurate with respect to the raw data if we want it to be useful. For example, if the number of males that are age 39 and have a specific disease is 39 in the raw data set, we want the synthetic data set to be close to this as well, or else the queries that we run on the synthetic data or the analysis that we run on the synthetic data may no longer be useful. Therefore, we use this intuition combined with prior work in the area of linear reconstruction attacks by leveraging novel conditional queries instead of using counting queries which were used in the past. These conditional queries encode the conditional relationship between the different attributes, and therefore they are able to leak out more information from the synthetic data than what has been done in prior work. We evaluate our attack against three main synthetic data algorithms sampled from different paradigms. Firstly, the Bayesian algorithm is sampled from the traditional statistical paradigm, whereas we use the CT-GAN algorithm from the machine learning paradigm. Lastly, we also use this RAP algorithm, which is a newer synthetic data algorithm from this select, measure, generate paradigm, which is a common technique that's used in synthetic data generation. We also compare our attack against two baselines for context. Firstly, the non-private baseline, where synthetic data is sampled at random from the raw data set directly, and also the INHIST algorithm, which first fits a histogram on each of the individual attributes, and then we sample the synthetic data from that histogram. What we find firstly is that when sufficient records are released from the synthetic data, powerful attribute inference attacks are indeed possible even against random records. As you can see in the graph here, where we are plotting the synthetic data size or the number of synthetic records released against our attack's accuracy, which are increasing for 3 out of the 5 algorithms that we tested. We also note that the CT-GAN and INHIST algorithms seem to be resistant to our attacks, but we'll explain this in the future. Next, we also compare our attack against prior attacks, both the memorization-based ones and Stadler-et-al.'s attack, and we find that our attack can outperform prior attacks in very specific settings. This is due to the way that our attack works in terms of queries and how the synthetic data is sometimes optimizes for different utility metrics. Next, we also look at the other side of the equation, which is about utility. We want to know how useful each of these synthetic data algorithms that we tested are. In order to do this, we focus on 2 error metrics that are popularly used in the US Census and also prior work that is evaluating the utility of synthetic data. This is the total variation distance, which is more of like a statistical distance between the synthetic and the raw data, and the mean relative error, which is basically if I ask a query on the synthetic data, how far away is it from the query on the raw data? And we plot this in the graphs shown on the right. What we find here is that actually there's an inverse relationship between the synthetic data size and the utility. For instance, as the synthetic data size increases, we find that the utility increases as well, although previously we found that the privacy decreases. Secondly, even though it seems like CT-GAN and INHIST are resistant to our attack, we see here that they have very large errors far outside what the other algorithms are producing, and therefore this privacy comes at a significant cost to utility. Lastly, we put both our findings on privacy and utility together, and we find that, and we ask the question about whether we can find good utility even while preserving privacy. In order to do this trade-off analysis, we arbitrarily define thresholds for privacy and utility, such as that the attack should not work on more than 60% of people, and that the relative error needs to be less than 20%. These thresholds can be changed as in different contexts. For example, with hospitals, you want the error to be much smaller, or in more general data set, you may be okay with having a larger error, but this is the thresholds that we define in our work. And in this graph, we know that both the accuracy needs to be small and the error needs to be small in order to have the ideal synthetic data that we want. The main thing that we found across two data sets and different settings is that no synthetic data algorithm is able to provide both good privacy and simultaneously good utility in any setting. And this is privacy even for the random records, not just for specific outlier records. Lastly, we look at the impact that differential privacy has on our analysis, and we find that for specific settings, differential privacy can indeed provide good privacy and utility, although this typically comes at the cost of vacuous theoretical guarantees, such as an epsilon of 100. Even though these guarantees are worst-case guarantees and they're not recommended to be used, for the average case, this seems to work pretty well. So in summary, our main findings are as follows. Firstly, we propose a new attribute inference attack on synthetic data that leverages aggregate statistics instead of relying on the memorization of whole records. Secondly, we find that when synthetic data is of sufficient utility, even random users can be vulnerable, not just outliers. Thirdly, we identify synthetic data size as an important consideration for privacy utility trade-offs, and this has not been looked at much in the past work, and we encourage data analysts to look into this in the future. Lastly, we find that DP can offer good privacy utility trade-offs in practice, although in limited settings, and practitioners have to do a case-by-case analysis on whether DP is a good fit for them. Thank you very much.